Alright, we're going to do an introduction to probability ideas. Okay, so what you're going to do here is talk about who will win the last banana, and this is a game. So you're on a desert island playing with dice with another castaway, and the winner's prize will be the last banana on this desert island. Okay, here are the rules. Each player rolls a die, so you're at home, you're going to roll 2 dice. If the largest value is shown 1, 2, 3, or 4, then player 1 is considered the winner. But if the largest value shows a 5 or a 6, then player 2 wins. Okay, so before we simulate this, okay, I want you to take a guess who you think has the advantage, player 1, player 2, and explain why you choose that reasoning. Okay? After you decide your choice, what you're going to do is actually simulate this. Okay, if you have 2 dice at home, track them down and play this game 20 times. Okay, if you don't, here's a link to a virtual 2 dice roller. You'll just have to copy that link. It's virtualdiceroll.com/2/n/2-dice. Okay, you'll pause the video, copy that, and then go simulate 20 times. Okay, so you roll it 20 times, and then you'll just tally whether player 1 was the winner, player 2 was the winner, and then based on those numbers, you can calculate the percentage out of 20 and answer questions A and B. Okay, so take care of all that for me, and then come back to the video when you're done. Alright, when we did this as a whole class, the proportion of everyone was 71 out of 180 for player 1 being the winner, and 109 player 2 being the winner. So based on our simulations of nearly 200 trials, it seems like player 2 has the advantage, which may or may not have been what you decided was supposed to happen on your guess. Okay, so what we're going to do is talk about these things, which you just did, both on number 2 and number 3, which is observed probability. Okay. Also sometimes known as experimental probability, because you're doing a series of simulations or experiments. Versus the true probability or the theoretical probability. To do that, you have to kind of draw out what's possible and then figure out which ones of those possible that we want to focus on. So this one, what we're going to do, it says we're going to focus on the true probability of player 1 winning. Okay, so first thing, underline this true probability. This is also called theoretical. Okay, but to do that, we're going to list out all the possible options that can happen when you roll 2 dice. So you could get a 1 with a 1, 1 with a 2, all the way through. We could get 2 with everything. And I want you to continue filling this out all the way through. Okay, each of these things that we're writing down right now are called outcomes because they are possibilities that could show up when we roll 2 dice. And together, all of these outcomes make up what's called a sample space, which is just a set of all the possible outcomes for a given situation. Okay, so I'm going to add some vocab here. This one single thing is called an outcome. And all of these together called the sample space. And sometimes this is written just in set brackets because it's the set of all outcomes. And sometimes it's written out in a table because it makes it more clear for what's going on. And what we're going to do is find the probability of player 1 winning. Okay, if we're talking about player 1 winning, we need the total number of outcomes first, and that's 6 times 6 is 36. And then player 1 was considered a winner if 1, 2, 3, or 4 was the highest value on either of the 2 dice. Okay, so that would be all the way through here. Sorry, I'm trying to highlight. So all the way through here, all the way down here, which is 16 out of the 36. Okay, and then again, when we're talking about probability, so I did this up here, but probability can be written as a fraction, as a decimal, or as a percent. But what's not allowed when we write a fraction is writing it in a form that's not reduced. Okay, so when you're looking at this, we want to take the 4 out of each and get 4/9. Or go ahead and write it as 0.4 repeating, or 44.4%. Okay, we don't want to leave it unreduced, so those are options. Okay. And a lot of times we're going to use symbols to talk about this. So I'm going to have you go back up here. And these two things that we're dealing with are different events. They're things we can measure. And so a lot of times they'll give letters to each event. So this is event A, and the second one is event B. So we would call this the probability of event A happening is 4/9. Okay? And if we compare that number, we hope that the closer probability was this one versus the one with only 20 different simulations, okay, because each time we roll 2 dice, it's called a trial, and the more trials we have, the closer your outcome should be, the observed value of the probability should be to the true or theoretical probability. And this is called the law of large numbers. Okay. I want to emphasize this is not what happens in practice every single time. Okay, it means that the more trials we have, as we increase the number of trials, these things are going to approach each other. Okay, so suppose I'm flipping a coin. Okay, I know the probability of getting heads is 0.5. But if I only flip it once, I'm getting either 100% heads or 0% heads. But if I continue flipping the coin, okay, the number of heads I see should end up evening out close to half of the total number of trials. It's not to say I get heads, 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 and then I say, well, I have to have tails on the next ones because these are supposed to even out. Okay, the law of large numbers says nothing about what happens in any individual trial. Anytime you flip the coin, it's 50-50. It says in the long run, these should be balanced out. Okay, you have a couple of questions on your homework that deal with those ideas. Okay, we're going to go over some vocab. We've already talked about a lot of this, but I'm just going to add some extra examples. A random process generates outcomes that are determined purely by chance. Okay, this is also called an experiment or a simulation. Okay, we did that with our dice, rolling them 20 times. And then a trial is just one repetition, so that's one roll of a die, or in our case, 2 dice. And then the law of large numbers, we said if we observe more and more repetitions of any chance process, as we keep repeating these trials over and over and over again, the proportion of times a specific outcome occurs approaches its probability. Okay, so this is our observed outcome, or observed probability. Okay, approaches the actual probability, the theoretical. A probability model is just a description of some chance process. This has the list of all possible outcomes and the probability for each. Okay, so I'm just going to make a really basic one. If we're talking about outcomes on flipping a coin, there are only 2 outcomes possible. Okay, you get a heads or you get a tails. And the probability for each of those is 0.5. So this is an example of a probability model. Okay, what's really important is when we're talking about probabilities, okay, a probability is a measurement of the number of outcomes that we're focusing on, so like heads, over the total number of outcomes that are possible, heads or tails, so 1/2 is 0.5. But probabilities, when we're measuring them, they have to be between 0 and 1. So all of these probabilities have to be possible. Okay, so I'm going to have you add it down here. Probability of something has to be between 0 and 1. It can be 0 if it's impossible to happen. It can be 1 if there's a 100% chance it is happening. Okay, but also, when you put these together, they should equal 1. They should sum up to 100% of all the options that are possible. All these options that are possible are called the sample space. And an event is any collection of outcomes from some chance process. Now, this is just something that you could measure the probability of. Okay, so say you're rolling a die. That's your experiment or your random process, and your event could be rolling a 1. Something you can measure the probability of. And that'd be 1 out of the 6 different outcomes. Okay? Complement rule says that this little notation means everything that is not A. So the complement is talking about when you have leftovers from some event. So let's go back to rolling a die and rolling a 1. Okay, the complement of if A is rolling a 1, the complement with that little c is not rolling a 1. And if we think about that, we know the probability of rolling a 1 is 1 out of 6. The probability of not rolling a 1 is the leftover 5. But you'll notice these equal 1. So if you know the probability of the first event, you can just take 1 minus that to get the probability of the complement. So that's the complements rule or theorem. Okay. 2 events that are mutually exclusive or disjoint if they have no outcomes in common. So this could be like rolling a 1 and rolling a 2. Assuming you are only rolling 1 die, these cannot happen at the same time, which means they are mutually exclusive. Now, complements, by definition, are mutually exclusive. Okay, rolling a 1 and not rolling a 1, those things cannot happen at the same time. Okay, but complements are more specific because they hit everything, whereas mutually exclusive just means they can't happen at the same time. So I want you to write that, can't happen at the same time. And if we have events that are mutually exclusive, then to find the probability of 2 things happening, we could add them together. Okay? So when we want to find the probability of A or B happening, I mean we could roll a 1 or roll a 2, you would just take your 1, 6 plus 1, 6. 2, 6 is 1/3, and say that the probability of rolling a 1 or a 2 is 1/3 in 1 roll of the die. Okay, so one thing that I'm going to add here is this word or. We have a math symbol for this. It's a union. So a lot of times you're going to see probability of 1 union 2 instead. Okay, so look out for that. Last thing you're going to do is just practice answering some questions with a probability model. Okay, it says why this is valid. Remember, there are 2 rules. These probabilities have to be possible, and they must add to 1. Okay, so based on that, go ahead and answer those questions A through E, then come back and check your work. Okay, 2 requirements. All probabilities are between 0 and 1, and the sum of those probabilities is 1. And mutually exclusive means they cannot happen at the same time. When they were asked this question, they were asked, how many children do you have? You're going to answer 2, or you're going to answer 1. You are not going to answer both. Okay, yes, you can have 2 children, and that implies you have 1, but this is a survey asking a question. You're recording the number. You're only going to answer this one way, okay, 1 or 2. Find the probability that less than 2. Less than 2 does not include 2, so it's just the probability of 1. Okay, that first one. Okay, 1 or 2, because these are mutually exclusive, we can just add. I want you to add this. We cannot do this if they're not mutually exclusive. That's what we talk about next time. And then this one does not have 4 or more children. This is how you're going to see complements, is this not. Okay, but you may have just added these 3 up, and that's valid. Okay, another way you can do it is using the rule 1 minus the probability of 4 plus, which means 1 minus the 0.13, and it gets you there a little bit faster, not with writing the notation, but 1 minus that 0.13 is faster than adding those three separately. Okay, we're going to use that sometimes when we're talking about complements, when we see like at least 1, meaning all but none, and use complements that way. But if I don't indicate to do something special, you're always welcome to just add those up if that's what you did normally. Okay, when we've got the table, it's not so bad to do that. Okay, your homework is on Sapling. Please come see me if you have any questions or get stuck on problems.